Welcome back to Practical PyTorch. Training a big network from scratch takes many hours, but someone already did that work. A pretrained network already knows edges and shapes, so we borrow it. We freeze its trunk, swap the head, and train only the head. By the end, you will beat training from scratch. In the last videos, we trained a small model from scratch. It learned edges and shapes from nothing. That took real work. Someone already spent 1,000 GPU hours learning those same edges. There is no prize for repeating it. So here is the plan. A pretrained network already knows edges and textures. We borrow that. Then we only teach it our two classes. This video has 3 parts. First, we freeze the pretrained trunk. Then we swap in a new head. Second, we train only that head. Just a handful of parameters move. Third, we race it against a model trained from scratch. Same data, same 5 epochs. First, we borrow the features. We keep the pretrained trunk and we replace only the head. Start on the left. An input image enters the network here. Next comes the trunk. This is a ResNet 18. It already trained on 1 million images. The early blocks learned simple edges and corners. The deeper blocks learned whole shapes and textures. At the end sits the original head. It sorts those features into 1,000 classes. One line loads all of it. Call ResNet 18 with the ImageNet weights. Now we freeze the trunk. Watch it fade to gray. Freezing locks its weights. Gradient descent cannot change them. The badge says requires grad is now false. The borrowed features are locked in place. One short loop does it. We turn off requires grad on every trunk weight. The old 1,000 class head is gone. In its place, a fresh head. It maps features to just 2 classes, ants and bees. The trunk behind it stays frozen. Only this new head can learn. One line builds it. Set model.fc to a linear layer, 512:2. So keep the learned features. Replace only the head. The trunk stays frozen while the new head trains. Second, we train just the head. Only a handful of parameters will move. The trunk is frozen, so only the new head trains. That is just 1,026 parameters out of about 11 million. Now watch the accuracy climb. Epoch 1, 64%, then 82, then 93. By Epoch 4, 94.12%, and it holds there. First the wrong way. Look, there is no freeze at all. The optimizer trains the whole network, so it overwrites those borrowed features. Now the right way. First we freeze the trunk. Then we swap in the new head. Only it will train. Build the optimizer after the new head so it includes it. The frozen trunk gets no gradient, so it is simply skipped. So freeze first. Even passing all the parameters moves only the new head. To fine-tune later, unfreeze with a much smaller learning rate. Third, does it beat training from scratch? Same data, same 5 epochs. Let's measure it. This chart shows both runs together. The transfer curve shoots up fast. It reaches 94.12%. The from scratch curve wanders low. It stalls at 64.71%. So transfer wins by about 29 points, and it trained about 10,900 times fewer parameters. Let's review. Keep the pretrained features. They already know edges and textures. Replace only the head. Size it to your own classes. Train that head first, with the trunk frozen. Only then unfreeze and use a smaller learning rate. Next, your own photos. Your turn. You build the optimizer over model.parameters. Then you replace the classifier head. Does the new head train? Pause and think. Okay, here it is. No, it does not. The optimizer only captured the old parameters. The new head came afterward, so it is never in the optimizer. It never updates and nothing warns you. Build the head first, then the optimizer. We just fine-tuned a pretrained network on ants and bees. Next time, you point this same recipe at your own photos. 2 folders, your own classes, an image classifier end to end. See you there.